Aerogel. Aerogels are a class of synthetic porous ultralight material derived from a gel, in which the liquid component for the gel has been replaced with a gas, without significant collapse of the gel structure. The result is a solid with extremely low density and extremely low thermal conductivity. Aerogels can be made from a variety of chemical compounds. Silica aerogels feel like fragile expanded polystyrene to the touch, while some polymer-based aerogels feel like rigid foams. The first documented example of an aerogel was created by Samuel Stevens Kistler in 1931, as a result of a bet with Charles Learned over who could replace the liquid in jellies with gas without causing shrinkage. Aerogels are produced by extracting the liquid component of a gel through supercritical drying or freeze drying. This allows the liquid to be slowly dried off without causing the solid matrix in the gel to collapse from capillary action, as would happen with conventional evaporation. The first aerogels were produced from silica gels. Kistler's later work involved aerogels based on alumina, chromia, and tin dioxide. Carbon aerogels were first developed in the late 1980s. Despite the name, aerogels are solid, rigid, and dry materials that do not resemble a gel in their physical properties. The name comes from the fact that they are made from gels. Pressing softly on an aerogel typically does not leave even a minor mark. Pressing more firmly will leave a permanent depression. Pressing extremely firmly will cause a catastrophic breakdown in the spar structure, causing it to shatter like glass, a property known as friability, although more modern variations do not suffer from this. Despite the fact that it is prone to shattering, it is very strong structurally. Its impressive load-bearing abilities are due to the dendritic microstructure, in which spherical particles of average size 2 to 5 nanometers are fused together into clusters. These clusters form a three-dimensional highly porous structure of almost fractal chains, with pores just under 100 nanometers. The average size and density of the pores can be controlled during the manufacturing process. An aerogel material can range from 50% to 99.98% air by volume, but in practice most aerogels exhibit somewhere between 90 and 99.8% porosity. Aerogels have a porous solid network that contains air pockets, with the air pockets taking up the majority of space within the material. Aerogels are good thermal insulators because they almost nullify two of the three methods of heat transfer: conduction, they are mostly composed of insulating gas, and convection, the microstructure prevents net gas movement. They are good conductive insulators because they are composed almost entirely of gases, which are very poor heat conductors. Silica aerogel is an especially good insulator because silica is also a poor conductor of heat. A metallic or carbon aerogel, on the other hand, would be less effective. They are good convective inhibitors because air cannot circulate through the lattice. Aerogels are poor radiative insulators because infrared radiation, which transfers heat, passes through them. Owing to its hygroscopic nature, aerogel feels dry and acts as a strong desiccant. People handling aerogel for extended periods should wear gloves to prevent the appearance of dry brittle spots on their skin. The slight color it does have is due to Rayleigh scattering of the shorter wavelengths of visible light by the nano-sized dendritic structure. This causes it to appear smoky blue against dark backgrounds and yellowish against bright backgrounds. Aerogels by themselves are hydrophilic, and if they absorb moisture they usually suffer a structural change, such as contraction, and deteriorate, but degradation can be prevented by making them hydrophobic, via chemical treatment. Aerogels with hydrophobic interiors are less susceptible to degradation than aerogels with only an outer hydrophobic layer, especially if a crack penetrates the surface. Aerogels are used for a variety of applications. Thermal insulation, with fiber-reinforced silica aerogel insulation boards' insulation thickness can be reduced by about 50% compared to conventional materials. This makes silica aerogel boards well suited for the retrofit of historic buildings or for the application in dense city areas. As other examples, aerogel has been added in granular form to skylights for this purpose. Georgia Institute of Technology's 2007 solar decathlon house project used an aerogel as an insulator in the semi-transparent roof. A chemical adsorber for cleaning up spills. Silica aerogels may be used for filtration, they have a high surface area, porosity, and are ultra-hydrophobic. They may be used for the removal of heavy metals. This could be applied to wastewater treatment. As a daytime radiative cooling surface that is designed to be efficient in solar radiation and thermal emittance. Aerogels may be lower in cost and negative environmental impacts than other materials. A catalyst or a catalyst carrier. Silica aerogels can be used in imaging devices, optics, and light guides. Thickening agents in some paints and cosmetics. As components in energy absorbers. Laser targets for the United States National Ignition Facility, NIF. a material used in impedance matchers for transducers, speakers, and range finders. According to Hindawi's Journal of Nanomaterials, aerogels are used for more flexible materials such as clothing and blankets. Commercial manufacture of aerogel blankets began around the year 2000, combining silica aerogel and fibrous reinforcement that turns the brittle aerogel into a durable, flexible material. The mechanical and thermal properties of the product may be varied based upon the choice of reinforcing fibers, the aerogel matrix and opacification additives included in the composite. Silica aerogel has been used to capture cosmic dust, also known as space dust. NASA used an aerogel to trap space dust particles aboard the Stardust spacecraft. These aerogel dust collectors have very low mass. The particles vaporize on impact with solids and pass through gases, but can be trapped in aerogels. NASA also used aerogel for thermal insulation for the Mars rovers. The U.S. Navy evaluated use of aerogels in undergarments as passive thermal protection for divers. Similarly, aerogels have been used by NASA for insulating spacesuits. In particle physics as radiators in Cherenkov effect detectors, such as the ACC system of the Bell detector, used in the Bell experiment at KEKB. The suitability of aerogels is determined by their low index of refraction, filling the gap between gases and liquids, and their transparency and solid state, making them easier to use than cryogenic liquids or compressed gases. Resorcinol formaldehyde aerogels, polymers chemically similar to phenol formaldehyde resins, are used as precursors for manufacture of carbon aerogels, or when an organic insulator with large surface is desired. Metal aerogel nanocomposites prepared by impregnating the hydrogel with solution containing ions of a transition metal and irradiating the result with gamma rays, precipitates nanoparticles of the metal. Such composites can be used as catalysts, sensors, and electromagnetic shielding, and in waste disposal. A prospective use of platinum on carbon catalysts is in fuel cells. As a drug delivery system owing to its biocompatibility. Due to its high surface area and porous structure, drugs can be adsorbed from supercritical CO. 2. The release rate of the drugs can be tailored by varying the properties of the aerogel. Carbon aerogels are used in the construction of small electrochemical double-layer supercapacitors. Due to the high surface area of the aerogel, these capacitors can be 1/2000th to 1/5000th the size of similarly rated electrolytic capacitors. According to Hindawi's Journal of Nanomaterials, aerogel supercapacitors can have a very low impedance compared to normal supercapacitors and can absorb or produce very high peak currents. At present, such capacitors are polarity sensitive and need to be wired in series if a working voltage of greater than about 2.75 V is needed. Dunlop Sport uses aerogel in some of its rackets for sports such as tennis. In water purification, chalcogels have shown promise in absorbing the heavy metal pollutants mercury, lead, and cadmium from water. Aerogels may be used to separate oil from water, which could for example be used to respond to oil spills. Aerogels may be used to disinfect water, killing bacteria. Aerogel can introduce disorder into superfluid helium-3. In aircraft de-icing, a new proposal uses a carbon nanotube aerogel. A thin filament is spun on a winder to create a 10-micron thick film. The amount of material needed to cover the wings of a jumbo jet weighs 80 grams, 2.8 ounces. Aerogel heaters could be left on continuously at low power, to prevent ice from forming. Thermal insulation transmission tunnel of the Chevrolet Corvette, C7. Camelback uses aerogel as insulation in a thermal sport bottle. 45 North uses aerogel as palm insulation in its Sturmfist 5 cycling gloves. Silica aerogels may be used for sound insulation, such as on windows or for construction purposes. It has been suggested that fogbank, a material of secret composition used in U.S. thermonuclear warheads, may be an aerogel.